All right, welcome back, class. So we're going to continue our discussion on chemical dynamics with a mind to trying to be able to understand and predict rates of chemical reactions. So we ended last time with a discussion of what first order kinetics was and the identification of the rate of a first order kinetic process, really meaning probabilistically the probability that a reaction has happened in some unit of time. And we thought a lot about what kind of sets the reasonable scale for units of time in molecular systems, some tau mole, which is on the order of picoseconds or femtoseconds. And we ended with a perspective, which was that chemical reactions don't take a long time on average because molecules move really slowly from reactants to products, but rather most reactions occur because of or through really improbable states. That to get from a reactant to a product, I need to break a bond or reorganize the molecular constituents in such a way which is a very high energy state and therefore very improbable state to access. And it's really waiting for that rare fluctuation that is what causes chemical reactions to take so long. And so we're going to flesh that perspective out today by thinking concretely about a case where we can compute everything exactly, namely a rare reactive event whereby we start molecules over on one side of a box, say this region A, that I've drawn over to the left, imagining we have some gas in that box. This is a box which has dimensions L cubed. And so from one corner of that box to the other corner, we'll denote that distance 0 to L. And the rare event, the reaction that we're going to imagine waiting for, is one of those tagged gas atoms wandering around this box and eventually finding its way through over to the other side. Filling up eventually this region B, which has similar size. So we'll denote some progress coordinates, some reporter on the position of that gas molecule as some point in this X direction. From 0 to L in X, it will be in the A state. From XB to XB plus L, it's in the B state, the B box. And intermediate, to get from A to B, what has to happen is that molecule has to find that small opening, which we'll denote has a cross section. This little tube has a cross section of area A. So again, to get from A to B requires a molecule undergo a rare fluctuation whereby it makes its way into that small constriction. And so we'll denote that midway point, X double dagger, it's where the molecule needs to get to in order for it to transmit from A to B. Now, we were actually going to start this B box completely empty, so we'll get rid of those particles over there and ask the concrete question, at what rate do molecules cross from A to B? Now, this is a nice physical reaction process or nice physical or mechanical process that we'll be able to compute everything explicitly for. But what you should really have in mind is that the mathematics we'll use to describe this process is going to be general, that instead of having a gas molecule over in some region, we could have some product or some reactant, like, as we discussed before, some isocyanide, whereby a methyl group is attached to some CN group that can, in principle, isomerize to a acetonitrile, whereby the methyl group is bonded to the carbon of that CN group. And in this specific process, the rare fluctuation that we're waiting for is that molecule to form this highly strained configuration whereby the methyl on the carbon group has broken the carbon-nitrogen bond and has started only forming the carbon-nitrogen bond. So that high energy, therefore low probability state is what we're waiting to see a fluctuation into in such an isomerization event. And in the case of the fusion, this physical example, the role played by the isocyanide is the gas molecule being an A. The role played by the acetonitrile is a molecule finding its way over in B. In the transition state is the molecule passing through this constriction, finding through a rare fluctuation itself in that pore. So again, the mathematics we'll use to describe a fusion will be able to hopefully generalize to things much more complicated like isomerization. So let's clean this up here a little bit. All right, like so. And so now roughly, if we were to try to just do a back of the envelope calculation to estimate the rate of a gas molecule going from A to B, we might suppose that that escape rate is whatever its typical, the molecule's typical velocity is. That's the speed at which it moves from one place to another generally, times then the number of molecules at that transition state. That would therefore report on the likelihood that the molecule finds its way into that constriction. Now, if we look at that number of molecules times the velocity, that can't quite be right, because the escape rates have units per time. So maybe a more nuanced estimate or guess might be that the escape rate, some effective effusion rate, is that typical velocity times the density at that transition state times A, that cross-sectional area. So A, units of length squared, multiplied to velocity, length per time, that gives me length cubed per time. Density at x dagger is then per length cubed. So indeed, I have something that has units of per time. So at least this has the right sort of unit. So this is what we should have in the back of our mind as what a kind of naive or back of the envelope, back of the envelope calculation for the escape rate might yield. So let's try to do this now more carefully. So the escape rate, as we've discussed, is slow, not because molecules move slowly, but because the probability of getting to that constriction is low. So let's denote the probability of getting to X dagger, P naught of X dagger. And it is something we expect to be small. So precisely, we'll define this P naught of X as the probability of a molecule position at X naught before it has escaped. So it's going to start over in that A region and make its way to that X position. Actually, we'll define this generally at any X. So we'll denote P sub naught of X as the probability of any molecular position before a molecule has escaped. It's a conditioning that says we're going to consider things in which all the molecules start over in that A box. And contrast that with P of X, without the naught being the probability distribution of X at the infinite time limit, or when the system has completely reached thermodynamic equilibrium. So molecules have escaped and then come back. Now in this simple system, we know how to compute P naught of X. It's equal to P of X divided by, or renormalized by, the integral of P of X taken from 0 to X naught. Or XB, that limit of the B basin, as long as X is less than XB, and it's equal to 0 otherwise. So that is to say, back in this cartoon, a molecule is going to be equally likely to be anywhere in the A basin, given it started in the A region or at equilibrium. So those two are equivalent in that region. But of course, if we are asking the conditioned question, what is the probability of being at some position before escaping? That means that those molecules have not yet reached the B region. So the long time limit probability P no sub naught of X will then have a different normalization constant, which we can account for through this expression here. Now that denominator is something we could work out explicitly. The integral from 0 to X of B of P of X is, to a very good approximation, just the integral from 0 to L dx P of X, because the probability of being in that constriction is, by construction, really very low. So that is then equal to the probability, or the integral over P of X over that region A. So it is the total probability of being in A. So this P naught of X has this form, which says that it is P of X, the long time limit probability, divided by the probability of being in the A region, since we can ignore the extension of that A region into that small constriction because it has such low probability. Carrying this through then, the probability of being at the transition state, say, divided by the probability of being in the A region, so integrating over all those positions. That is something which the probability of being in that specific transition state. Now, this is another one of those awkward cases where x being a continuous variable, we need to worry a little bit about how we count. So really, we could think about the probability of being in that transition state in some small additional region delta x, so counting spaces up in little boxes of delta x. Instead, what we'll do here for simplicity is just divide that p of x dagger by some reference point, being, say, p at relative to p of x is equal to L over 2. And if we do that in the numerator and the denominator, then ratios of probabilities don't have that same awkwardness associated with continuous variables. So those are then two ratios that we can compute exactly. So if we go back up to our little diagram, we are now asking for the probability of being, use a new color, exactly here at that value of x relative to being at some point x over 2, or L over 2, excuse me, in the A region. So if molecules are equally likely to be anywhere, then that relative probability is just the multiplicity, the number of ways that I can be at that region x dagger compared to the number of ways I can be at x is equal to L over 2. Well, that's just then counting up the number of ways is then just asking, well, how many different states are there going to be in those orthogonal directions, say in the y and z directions, at x dagger relative to L over 2? And that is then just their areas, which at x dagger is that cross-sectional area of the tube A relative to the cross-sectional area of the whole box, L squared. Now, the integral over the A region, that's going to give me if the probability is uniform in the box, then integrating over all of the ways I could be in that box, and if every way is equally likely, then that is just the volume of that box. I have the same cross-sectional area at L over 2, so that's the volume of that box over L squared. Let's give it the volume of that A box. Those L's over 2's cancel, and I'm left with that the ratio of probabilities, the likelihood that I am at x dagger relative to being in anywhere in A, is the ratio of the cross-sectional area of that tube divided by the volume of that box A. So we'll denote that as P naught of x dagger. Let's clean this up a little bit and get it better centered. Good. So now we have just computed the probability of having that rare fluctuation that takes a molecule from A and gets it to that transition state, the center of that constriction, which is the kinetic bottleneck that that molecule has to pass through in order to make its way over in B. From that, it should be clear we'll be able to compute the number of molecules at that position if those molecules are uncorrelated, like we are going to imagine for a dilute gas. So that's going to be part of that rate. The next part of the rate has to be associated with how fast molecules move from A to B within that constriction, say. One way to ask that question is to say, ask specifically, how many molecules cross x dagger in some short time delta x? No, excuse me. how many molecules cross X dagger in some short time delta T. So a way to think through this is to note that those close enough to X dagger and moving fast enough are only going to be those molecules that can cross in a short enough time delta T. So I think it makes this clear if we draw a little diagram. We're imagining X increasing in that direction. Here's our X dagger. We're asking, in some short amount of time, delta T, how many molecules pass through that plane? And so if I'm a molecule, say here, if I'm going at some speed Vx, and I start at some initial X, well then the displacement over some small time is going to be X plus V times delta X. So that was one, for example, that could cross X dagger. A molecule starting too far away, going at the same speed, reaches only X plus Vx times delta T, which is then, say, less than X dagger. So I have to be close enough to X dagger, provided some typical speed, Vx, in that delta T to pass through the plane at X dagger. Now, if I am over on the other side and moving in the opposite direction, those are also ones that I'm not going to count, because I'm asking this conditional question of how many molecules go from A to B, not the flux from B back to A. So those are ones that I'm not going to count. So for a given value of that velocity, the crossing probability is going to be that given by integrating from X dagger minus Vx times delta T up to X dagger, integrating the probability of being at one of those values of X. So that is to say that I can include all of those particles that start far enough away that in the time delta T for a given speed Vx, they will make it across X dagger. Molecules at exactly X dagger then only need an infinitesimal speed to move to make it across that plane. So the number of molecules for a given speed that will cross X dagger will be given by integrating all of those molecules over the range set by that Vx times delta T. Now that is equal to first order, the probability of being at X dagger times Vx delta T. That is to say that molecules moving with a constant speed over a time delta T have to be, again, close enough to X dagger to have made it across. So we can assume that that probability is not, that delta T is taken small enough that that probability is just constant and therefore just evaluated at X dagger. Now we know that molecules move at different speeds at thermal equilibrium. So the speed is something we have to also average over. So if we take an average over Vx, well, the possible values that Vx can have are minus infinity to infinity. We're averaging Vx. We need the probability of Vx. We're averaging the function Vx p naught x dagger delta t, but of course those are constants, and the probability of seeing some specific velocity in thermal equilibrium is completely independent of the probability of seeing some position, so those probabilities factorize. Another way to say that is we can independently average over those thermal velocities, and that then we will get is the probability of being at x dagger delta t over 2, and the average of Vx. So we can write this, let's do this in 2 steps. So we can pull the p naught x dagger out of the integral times delta t. We're left with the Vx times the probability of seeing some velocity. Now, if we just do that integral, p of Vx is something we know as the Maxwell-Boltzmann distribution. Averaging V will just give us 0, but we don't want to average V by itself. In fact, we want to average only those particles that are moving in the right direction. So we want to average only the positive velocities, or because the Maxwell-Boltzmann distribution is symmetric, if we average the absolute value of Vx and divide by 2, then we'll get the same answer. So this is going to give us the correct average velocity for particles moving from A to B. And then that is just a thermal average of the absolute value of Vx, which is a quantity that we all know, 1/2 times the average value, absolute value of Vx, can be computed from those Gaussian integrals we were thinking about early on in class, and will give us a factor of kBt over 2 pi m, all under the square root. So that's an old result we derived long ago for Maxwell-Boltzmann distributed velocities. So putting this together, the number of molecules entering B, then per time and per unit area is equal to, well, the number of molecules entering B is going to increase with the number of molecules in A. We have A over VA as the probability to have had that rare fluctuation that takes the molecule into that constriction, per the number of molecules passing through that constriction in some time delta t was delta t times that average velocity, which is then kBt over 2 pi m, all under the square root. If we now ask the question per unit time, so per delta t, and per unit area, per A, those A's will cancel, the delta T's will cancel. A over V is then just the density in A times then that thermal velocity, or kBt over 2 pi m. So the rate of molecules per unit area entering B is proportional to how many molecules start in A times those characteristic velocities that particles move with, which is thus just the thermal velocity, average thermal velocity. So this is something that is proportional to mass to the 1/2 minus, due to those thermal velocities scaling like that. Now this is actually something which has a well-known name. This is something known as Graham's law of effusion. It seems like a kind of oddly specific question to ask. How do molecules move from one box in the other, given they have to pass through this little constriction? But it is actually of a significant amount of practical use, and was historically used here in Berkeley about, let's see now, about 70 years ago, 70 or 80 years ago. This effusion process was what actually people developed here in order to separate elements, different isotopes of different elements. Isotopic separations are those which are often difficult to do chemically because isotopes react in the same way often, and yet this physical process differentiates molecules based on their mass. The rate of this diffusion goes down with mass to the square, with the square root of the mass. And so molecules with different masses will escape at different rates. So for example, if I had isotopes of uranium, say uranium-238, if I made a ionic compound with it and fluoride-6, which is what was developed by people like Seaborg here, and a compound of uranium-235, which of course is the isotope of uranium that people were caring about at that time. The fact that there is a mass difference, an atomic mass difference between those two of 3 units means that you could separate those two with this effusion process. The exiting gas, for example, in this case, would be enriched with uranium-235 by a ratio that was computable, the ratio of M1 to M2, which in this case was about 0.4%. Not a very large enrichment, but one which was useful, one which was useful enough to have the US government make giant effusive tunnels that people built to actually separate out uranium-235 from uranium-238, because other chemical separation techniques just weren't useful or were not usable. Okay, so that's a little bit of an aside. It's worth kind of thinking back what approximations we made in order to arrive at this rate of this effusive process. Well, we assume that all molecules that cross through X dagger left to right will enter into that B region. But of course, that need not be true because of collisions that molecules could undergo with other molecules or with the container. So imagine looking at that little pore, drawing that boundary at X dagger, and imagining a molecule that we counted as part of the flux through X dagger at some point in time. Imagine another molecule whose flux we did not count was going in the opposite direction. Those two molecules could collide, bouncing off of each other, and even though it was in the absence of that second molecule going to flux through X dagger due to that collision, may not. That was a process that we didn't consider. We assumed that all molecules going in the right direction stayed going in the right direction, eventually entered into B. In fact, this sort of collision process could have happened much further down the tube, resulting in that molecule taking a long time to return back to A, but eventually do returning back to A. This is a process that more generically is known as a recrossing event, and it would lower the escape rate. Lower the escape rate because it's a contribution to the flux that we shouldn't have counted. So the effective flux of molecules starting in A and going to B should have been lower than what we assumed it was. It's reasonable to ask how much would this recrossing change the escape rate? And that's actually quite a difficult question to answer because it would depend on things like the density in that pore, how many molecules there could be. It would depend on the length of the tube. Longer tubes will give more opportunities for molecules to collide, thus redirecting their motion. And so while it's easy to estimate this kind of maximum escape rate in neglecting recrossing events, correcting for that is quite hard. But if we assume that those recrossings are small, written generally, what we learned by studying this diffusion process is that the effective rates, or the probability molecules enter into B, per unit time, it had a pretty simple form. It was 1/2 the average velocity in that direction times the probability of getting to that transition state, in this case the constriction, the small pore that connected A to B, over the total probability of being in A. So it's a ratio of probabilities of starting in A and getting to that transition state times the average velocity that molecules move with, and the factor of 1/2 comes from averaging only the molecules moving in the positive direction. Looking at this form, we derived it thinking about diffusions, but this should actually help us understand actual chemistry if we generalized it just a little bit. So let's return to chemistry. What does this mean for chemical reactants transforming into different molecular products? So again, we imagine that the reason why chemical reactions take a long time is that they have to overcome some high energy barrier. They have to transverse some very low probability states. So a way of characterizing that would be to think of the free energy as a function of some abstract reporter on the progress of some reaction, some reaction coordinate, something that will distinguish states A from states B. If states A, if the, say A is some reactant molecule, if it is long-lived, that means that it resides in some free energy minimum. Similarly, if B is some product, and if it too is long-lived, it resides in some other free energy minimum. If the rate to go from A to B is low, that means that there is a barrier separating A and B, and that's, in a more chemical example, what we mean by the transition state. It's that highest point in the progression of some reaction, the kinetic bottleneck that atoms have to pass through in order to transform from reactants to products. We can denote that barrier height as delta G dagger, quantifying just how high in free energy that transition state is relative to the basin that the molecule is starting in, the reactant basin. From our fusion analogy, we might expect then that the rate of some process that takes reactants A to products B is proportional to the probability of getting to that transition state divided by some characteristic timescale, say, to fall down into that B basin. Let's call that tau descend. The probability of getting to that transition state will, free energies tell us about the probabilities of groups of microstates. The transition state is not a single microstate, rather a collection of microstates. Therefore, the probability of getting to that set of states is thus proportional to that free energy difference. If we follow that strategy of the effusion calculation, we have to think a little bit more carefully about what exactly plays the role of X. So that's the first question we have to ask. X was a coordinate that distinguished where we started from, the A box, from where we ended up in the B box. So more generically, we can define something called a reaction coordinate. Let's give it that symbol, not to be confused with the electric field. It's going to be some set of coordinates, some parameter that we can compute that describes the motion that advances a reaction. For example, in our isomerization reaction, it's something that would tell us about maybe the angle that methyl group makes with a carbon-nitrogen bond. So as I pass through the transition state, that angle changes significantly before ending up with a bonding topology where that methyl group is attached to the carbon group. So that's some set of angles and bond distances. Maybe the bond distance is a good example of one. In the isocyanide group, that methyl group is attached very closely to the nitrogen. As the reaction proceeds, that distance gets further away. In fact, that's easier to see in simple models of dissociation, or simple examples of dissociation. Say I have HCl. I can define a reaction coordinate that will tell me about that dissociation just by knowing something about how far the hydrogen is from that chloride. The reaction progresses, dissociation advances by that distance getting larger. Now, reaction coordinates are a very subtle business. People have to think quite hard about, for a specific reaction, how best to describe that reaction coordinate. Imagine, for example, asking a different dynamical question. Say, how does an unfolded protein fold? What would be the reaction coordinate that would describe that process? That is some much more complicated sets of angles and distances. In fact, there are probably so many angles and distances, that's not a useful way to describe that reaction. Rather, a reaction coordinate might be the number of favorable contacts made as that native structure is forming. It might, for example, if that protein is very hydrophobic, might need to know something about what the solvent is doing. If the solvent has to get out of the way, if water has to get out of the way for that hydrophobic pocket to collapse or core to collapse, the reaction coordinate that tells me about the progress of the reaction might need to include those solvent degrees of freedom. If we think about the process of nucleating a liquid from its vapor, ooh, I got a better idea. Let's make that some liquid droplet. So that's some, say, water vapor and some water droplet. You might imagine that in this case, the reaction coordinate is something to do with the number of liquid molecules or the size of that droplet. As we discussed when we discussed classical nucleation theory, talking about how you grow a droplet in a vapor, that process proceeded through a barrier as well. I needed to grow a large enough droplet for that droplet to be stable. So the kinetic bottleneck, the transition state that I have to pass through, the improbable fluctuation has to be, in this case, maybe the size of some droplet that has to form. So if we're going to carry through is a calculation which encodes more chemical information, how specific sets of reactants go to specific sets of products, which is in the spirit of the effusion calculation we did today. We have some sense of the first step, what's going to play the role of X, the reaction coordinate. Now we just need to fill in the details of how should we think about the probability of getting to that specific value of a reaction coordinate, and also how to think about the flux over that barrier or through that plane defined by the reaction coordinate. So those are details we'll fill in the next lecture, where we eventually arrive at a very specific form for an estimate of a rate of some reactive process. All right, so stay tuned for that.